Hello. Okay, so I did a little bit of edits between streams, mostly just fixing up the wording and stuff of all the theorems that we wrote the other day. Although I did add one extra major proof, but we can go through a recap real quick. So yesterday, we started on this section for power series. I've actually changed the name to exponential growth and power series in Analogicity, because this whole section is going to be all three of these concepts. So of course we have, a power series has this form. It's a polynomial but with infinitely many terms. We have our definition of an analytic function is a function where it has a power series at each point that converges in a neighborhood to the function. And we've defined this function, this capital Phi function, to sort of analyze how things are growing with respect to some exponentials. So I've added and updated some theorems and results about this capital Phi function. It's mostly the same as yesterday. I've just made it a little cleaner. So the first thing we have is we have this theorem here. It's a short one, which basically says so this capital Phi is a function over sequences of coefficients in our space A. And this first theorem says if that sequence happens to actually be on the complex plane, then this capital Phi function is actually just the root test. So it's just the limit. Actually, this should be limit supremum. Let me fix that real quick. So it should just be limit supremum of the absolute value of the nth root of alpha sub n. So if it's a complex number, it's literally just the root test. But in general, for any alpha sequence of coefficients in our general space, not necessarily complex, phi of alpha is just the supremum of the phi of the projections. So it's the supremum root test of all the projections. So that was sort of how we had that before. And the proof for this is straightforward. So we proved this part first for the complex series. So if it's complex, then for every index k greater than 1, this projection is just 0. So that's sort of our definition of how our complex numbers fit into our space, is that the higher projections of a complex number are just all 0. Because all of these are 0, of course, these higher projections of some complex number, even if we take their absolute value and we take the nth root, that's still 0. So the lim supremum is 0. And because because all of these supremums are non-negative, and because we have our capital Phi function is defined as the supremum of all these projections, these lim supremums are the projections, it follows just by this definition that phi of alpha is just this first expression. So if we take a supremum of a bunch of non-negative things, and all of them except for the first one are 0, then it's just the first one. That's pretty straightforward. In order to get to this second claim, it actually just follows immediately from the definition. Each of these projections is a complex sequence. So if we take alpha and we take its kth projection, that becomes a complex sequence then. And this is just the root test on some complex sequence. So this is just phi of p sub k alpha, this term specifically inside the thing. And then, of course, by definition, phi is just the supremum of all these. So it's just the supremum of the phi of the projections. So that's sort of where we left off. with that, I've updated some of the theorems. I've also added a proof for these different characterizations. So we had these three different statements, these three different characterizations of this capital Phi function. So the sort of the default definition is this lim supremum definition of this root test. But we also have the other two characterizations that we stated. Before we didn't have proof for these, but I sort of added one in between. It was mostly just sort of, a lot of analysis, but we can go through it. So the second characterization is that phi of alpha is the infimum of positive real lowercase phi, such that this limit ends up being 0. So this limit is alpha sub n times phi to the power of negative n. So the second characterization is basically saying, what's the smallest sort of real value, such that if we multiply this by a decaying exponent with that base, that this is going to be 0. The third characterization is saying, instead of having these limit to 0, it's saying, let's find some coefficient a, which is all real components, such that for every index, for every point in the series of this alpha sub n series, the absolute value in terms of a of this alpha sub n is bounded by just a times this phi power n. So what's sort of the first one is saying, what's this root test? The second one is saying, how can we make this go to 0 by multiplying it by some real geometric thing? And the third one is saying, how can we bound this by some real geometric thing with some coefficient? And the proof is, we use this, actually you can see here the conclusion that we build up to is we're going to show that the phi 1, the first characterization, is greater than or equal to phi 2, the second characterization, and phi 2 is greater than or equal to phi 3, that's the third characterization, and then we're going to prove that phi 3 is greater than or equal to phi 1, which is the first characterization again. And by proving all three of these inequalities, we get sort of this circular chain of inequalities, and that lets us conclude that they're all equal, because we have this sort of circular way of talking about them. Nice. Yeah, so this is just three separate proofs, one for each of these inequalities. So the first one is, actually they're all very similar. For each of these three parts, we take some real number, lowercase phi, which is greater than one of the characterizations. So in the first step, we take this phi greater than phi 1. In the second case, we take this phi greater than phi 2. In the third case, we take this phi greater than phi 3. And then the conclusion of each of these parts is also the same. It's eventually we find out that here we had every phi 1 greater than every phi greater than phi 1 is also greater than or equal to phi 2, and that gives us phi 1 greater than or equal to phi 2. And same thing over here, every phi greater than phi 2, as we're going to end up proving, is greater than or equal to phi 3. So also phi 2 is greater than or equal to phi 3, and then this third one is also the same. And then there's just some nuance of how we get to that point. So for the first one, we take our phi greater than phi 1. So by this phi 1 characterization, because we have this lowercase phi greater than phi 1, we can also find this var phi. So because there's this strict inequality, we can find some other var phi in between them. So we sort of fit something in between these two things. Once we have this one, by this definition of phi 1, for every index k in natural, we have this var phi as being strictly greater than this lim supremum. So because this phi 1 is the supremum of all these limits, because of this var phi is greater than, is greater than that, then it has to be greater than all these limit supremums. So var phi is strictly greater than this limit supremum. But because it's a limit supremum, that means that there is some lower bound on these indices n. There's some lower bound, capital N, after which all these little n's greater than capital N are going to have this strict inequality. So phi is going to be strictly greater than this root. That's because we're taking the limit supremum of these roots. So eventually, if this limit supremum is less than var phi, then eventually they're always going to be less than var phi, eventually. But if we have this thing, what we can do is we can just solve this around. So if we multiply both sides of the equation by this other phi, power negative n, and remember, this other phi is greater than var phi, and it's also greater than phi 1. So we sort of fit these in between. So if we multiply both sides by this phi power negative n, then we get, and we can also raise, so we raise this to the power of n, and that's how we get no exponent on this term. That gives us this var phi power n, and then we multiply by phi power negative n, which is here. And that just gives us this projection term times phi power negative n as being strictly less than var phi over phi power n. But because, right up here in our selection of our phi, we have this phi greater than this var phi, so their fraction is less than 1. And because their fraction is less than 1, we're raising them to some, and they're positive. That's also important. So because their fraction is less than 1, and we're raising them to this integer power, and we're making that integer very large, as we keep multiplying by something less than 1 over and over again, that's going to limit to 0. So we end up with this fraction, this power n, limits to 0, but this bounds, right? This bounds this term, which means that this term also has to go to 0. And because this term is going to 0, since this is true, so this was true for each of these indexes k, so we said this is valid eventually for each index k. This lower bound doesn't really matter for the limit. Yeah, it is a lot of phi. Yeah, so this lower bound doesn't really matter for the limit. So we're saying eventually this is less than that, and because this term with this exponent is going to 0, then this term is also going to 0 with n. And this is true for every projection k. Because it's true for every projection k, that this expression is going to 0. So because our projections are linear and phi is real, we can actually just pull this exponent inside the projection to get p sub k of alpha n times phi power negative n. And because this is true in every projection, then actually this alpha sub n times phi negative n, this is going to 0. But that's just our second characterization, right? We have this limit of these alpha sub n times phi power negative n going to 0. So this proves that this phi value, this is greater than or equal to this phi 2, because it's an infimum across all the phi which satisfy this. So of course this phi can't be less than that. And so that's the first part. Since we only required phi to be greater than phi 1, then we have this inequality. By taking this as low as possible, we get this phi 2 is less than or equal to everything that's greater than this. The next part of the proof is we take phi greater than phi 2. Since by this second characterization, if we have this lowercase phi being greater than this capital phi 2, then this limit has to be 0. So alpha sub n times phi power negative n limits to 0. That also means, just like before, for every index k, we have this projection limiting to 0. So if this term limits to 0, then it limits to 0 on each projection, which means that all of these projections here limit to 0. So because this is true, we can find any real value. So we're going to select this value. We're going to select some value which satisfies that this is greater than or equal to the supremum of all these terms. This is possible because, so this term here, this term here, this is real because we have this absolute value times this real thing, and it's limiting to 0. So eventually we can sort of, eventually find a point where it's never going to exceed, and we can just select this p sub k of a to be greater than or equal to that supremum across all the terms. Because this gives us a selection for this p sub k of a for every k, then we've essentially selected a. So for every integer n and every index k, we get this projection, so this term here, the k projection of alpha sub n times phi power negative n. This is less than or equal to p sub k of a, and consequently, if we multiply through by phi power negative n, then we get this p sub k of this absolute value of alpha sub n, this is less than or equal to this p sub k of a times phi power n. And that just happens, we just multiply through by this phi power n. But because we have this inequality on every projection, right, that just means we have this precession relation instead, which is just pointwise inequality, which is what we have here. So this absolute value of alpha sub n is bounded by a times phi power n, but that's exactly the definition of phi 3, which is that for every n, so there exists some a, which is real on each index, such that for every n, absolute value of alpha sub n is bounded by a phi power n, which is right here. So instead, we also get this phi is greater than or equal to capital phi 3. And just like before, because the only restriction on this lowercase phi was that it's greater than phi 2, then everything greater than phi 2 is greater than or equal to phi 3. So we have to have phi 3 less than or equal to phi 2. And the last part of this proof is if we take any real phi greater than phi 3, just like the other two parts, we can find, so by this third characterization, we can find this a, some real sequence, some real coefficient in a sub r, such that the absolute value of alpha sub n is bounded by a times phi power n for every n. Then, for each of these indices, k, we can take this projection, so the absolute value of the projection on k of alpha sub n is now bounded by p sub k of a times phi power n. And then we just solve this in reverse. So we take the nth root and we get this absolute value of this projection. If we raise this to the power of 1 over n, this is less than or equal to this projection p sub k of a to the power of 1 over n, and then times phi. In the case p sub k is 0, then all of these roots are just 0 constantly. So this would, this one would go to 0. Otherwise, if this is not 0, so this is just a standard limit of real numbers, this would go to 1. But in either case, when we take the limit supremum, this is going to be at most 1 and at least 0. It's going to be positive, which means that when we take this term in limit supremum, this limit supremum of this nth root is less than or equal to phi. But this is true for every index k, and this is just the first characterization, this nth root test. Because this is less than or equal to phi for every index k, then this phi is actually greater than or equal to phi 1, and because phi was any number greater than phi 3, then we have to have phi 3 greater than or equal to phi 1. And that sort of concludes the proof, is that now we have this sort of circular chain of inequalities. Which gives us the ultimate equality of all three of the characterizations. Anyway, so so that's that proof. So that proves that all these three characterizations are the same, which is super useful. Oops. So now that we have all these three characterizations are equal, we can sort of use these however we want. So this first one, again, this is the root test on each index. That's the first one. The second one is the smallest phi, where the infimum of phi, where this limit tends to 0. And the third characterization is, can we find some coefficient so that this series can be bounded by just this coefficient times some geometric term. So all these three are equivalent. So whenever we want to use these in proofs, we'll just refer to them as the first, second, or third characterization of this phi function. So our immediate corollary for this is we have a couple. If we have any series and a constant which is non-zero, then the phi of alpha is the same as phi of c times alpha. So if we scale up our sequence by some constant c, the phi value doesn't change. And the proof of that is really straightforward. It follows really quickly from the second characterization, which is this one right here. So the infimum of this alpha sub n times phi power negative n tending to 0. We know that if we take this term, this will converge if and only if, when we scale this up by c, it'll converge. That was one of our earlier theorems. So if we multiply something by c, which is non-zero, it'll converge if and only if the original thing converges. And of course, if it converges, if either of them converge to 0, then both of them converge to 0. And that also follows from the zero product property and the fact that multiplication or product is continuous. So this will converge, so this C times alpha sub n, this will converge to 0 if and only if alpha sub n does. And actually we can make this a little more clear. There we go. Yeah, so so these terms were, oh gosh, it won't render. There we go. Okay. Where were we? Yeah, so this will converge if and only if this converges, and this will converge to 0 if and only if this one does. And then the second characterization just gives us the result pretty immediately. The second corollary is that this phi function is monotone. So if we have alpha sub n, if the absolute value of alpha sub n is bounded by the absolute value of beta sub n for two different sequences, alpha and beta, then for every n, this phi value of alpha is also bounded by the phi value of beta. And that follows immediately from the third characterization, right? So the third characterization, right up here, that's can we find a coefficient to bound the absolute value of the sequence? And of course, if alpha sub n is bounded by beta sub n, then anything that bounds the absolute value of beta sub n will also bound the absolute value of alpha sub n. So the phi value of alpha has to be less than or equal to the phi value of beta, because we can just use the same exact coefficient. So whatever we use for beta, we could use for alpha as well to get that bound. So here we just have some text describing. So we've gone through all of this sort of. Yeah, that's great. Yeah, I was thinking that'd be really good. In the future, I want to see if it's possible to make it so that I can get like live updates. I don't know how that's possible, but I think that would be really exciting. If you could like follow along with the updates as they happen as well. That would be really neat. But yeah, it's very good. Okay, so now so we proved this thing. So here we just have some pontification where we're saying in advance, we're sort of saying the convergence of a power series can be determined by this phi function. So just like in real or complex series, you just use the root test, and that tells you read-only permission. That might work actually. I'll try that in the future, or maybe when we start editing in a few minutes. But yeah, so just like real power series or complex power series, you use the nth root test to find the radius of convergence. We're sort of stating in advance that we're going to find the same thing, that we're going to have this radius of convergence. So we have a couple of lemmas first, and I've stated these in a way, these different corollaries and lemmas in a way that makes this ultimate result a lot easier. This is a lot easier to follow, hopefully. So the first lemma for this next upcoming theorem is sub-additivity of phi. We've sort of gone over that one before. We just use the second characterization, which is based on limits tending to 0. So if we have some phi greater than the max of these phi values, both of these limits will tend to 0. And then because of the linearity of limits, this is just the limit of their sum, which means that the phi value of the sum is less than or equal to the max of this phi value of either one. And then, of course, by taking the infimum. The next one after that is sub-multiplicativity. We also did that one, and that uses the sub-multiplicativity property of the a function, the script a function. So using the third characterization of our phi function, that's the one where we have bounds. So we have some bound on some real exponential with some coefficient upper bound. So using here we are, 3.4. Using the third characterization, we find our phi 1 greater than phi of alpha, phi 2 greater than phi of beta. Then we find our coefficients a and b to bound these terms. So alpha sub n is bounded by a, phi 1 power n. Beta sub n is bounded by b, phi 2 power n. And then we just sort of multiply these together. So a of absolute value of alpha times beta is bounded by absolute value of alpha times absolute value of beta, which is then bounded by each of these bounds. So b times phi 2 power n times a times phi 1 power n, and then we just rearrange them. So we have a times b times phi 1 phi 2 power n. Because this bound is true for every n. This is just a third characterization, which is capital Phi of alpha beta is bounded by phi 1, phi 2, the product. And then just by taking these phi 1 and phi 2 to the infimum, remember phi 1 only had the restriction that it's greater than phi of alpha, and phi 2 only had the restriction that is greater than phi of beta. So the phi of the product alpha beta is bounded by the product of the phi values. So that's the sort of the sub-multiplicativity property of the capital Phi function. The next lemma, which is the last lemma before the theorem 3.6, is this sort of rising falling sum thing. And this one's a lot shorter than it used to be, because it turns out to be really quick. So we take our phi value greater than the max of the phi values of alpha and beta. We find our binding coefficients through using the third characterization. So alpha sub n is bounded by this geometric series, and beta sub n is bounded by this exponential series for every n. And then we just use the triangle inequality for the a function. So a of this, so that you have this sum of these alpha sub I times beta n minus I. This is bounded by the sum of the absolute values, so absolute value sum, bounded by sum of the absolute values. And then that in turn is bounded by the sum of the product of absolute values, so absolute value of alpha sub I times absolute value of beta sub n minus I. And then because each of these terms, absolute value alpha sub I and absolute value of beta sub whatever, is bounded by these other terms, we have a times phi power I, b times phi power n minus I, and then just by factoring out these phi values, right, the powers of I just cancel out, and we just get phi power n, which is constant with I, and we can also factor out the a and b, and then the summation is just the summation of I from 0 to n of just 1. So this is exactly equal to a times b times n minus 1, n plus 1 times phi power n. And then we can just use, so again, because the capital Phi function for real series is just the root test, we know that the phi value of n plus 1, that's just a linear function, so its phi value is 1. You can work that limit out if you'd like. It's sort of a standard calculus limit. It's really similar to n to the power of 1 over n, except in the base we just have n plus 1 instead of n. But it's essentially the same proof. So because we have this phi value is 1, we use the fact that when we have these coefficients in here, if we take the phi of some constants times some other expression, these constants don't really matter. If they're non-zero, then it's equivalent. If they're 0, then it's 0. And so we have this less than or equal to relation. So we just sort of take these constants away, and we just get this phi value of this is less than or equal to the phi value of this product, so n plus 1 times phi power n. Because we have phi of n plus 1 is just 1, we use the sub-multiplicativity property of the phi function to give us that this phi of n plus 1 times phi power n, this is bounded by just the phi of the exponential series phi power n. And of course, if you do the root test on an exponential series, you just get the base, and that's phi. So from the monotonicity of the capital Phi function, so over here on the left side, we have the absolute value of this whole summation series is bounded by the absolute value of this other series, which means that their phi value of this summation is also bounded by the phi value over here. But we just calculated the phi value as phi, lowercase phi. So from monotonicity, the phi value of this whole summation is less than or equal to this lowercase phi. And because we only restricted phi to be greater than the maximum of these two terms, then we can just take it to the infimum and we get the result. So this rising falling sum is bounded by the maximum of the phi value of this one and the phi value of this one. Whichever one is larger will bound this summation. And that makes this theorem, all these corollaries and lemmas, makes this theorem really easy. So this theorem is, for each x in our space A, this series of exponentials, so x power n, if we take the phi value of that exponential series, we just get the absolute value of the first projection, the first component. And the way to prove that, so first we start by making this inductive formula, which we did before. So we actually, this inductive formula over here. So we start out with, we pick some index k, and we pick some n greater than 0. Because n is greater than 0, so if we take x power n, and we project it down onto the k-axis, we can, because n is greater than 0, we can sort of split this up as x to the power of n minus 1 times x. And then if we expand the definition of Dirichlet product, that gives us this summation across these terms. And then we just take out the term where a is equal to k. So because this is running through all divisors a, b, which multiply up to k, we can just take out the term where a equals k. And that gives us this expression, plus this other remaining term, this other remaining summation. But here, right, so we started with the kth projection of x power n, and we ended with the kth projection of x power n minus 1. But this just lets us do an induction, right? So if we just have this, apply this formula again to here, we'll get this summation times some other second summation times the power of p1x and so on. So if we just use this sort of replacement in an induction across the n values, that'll give us this general formula. So pk, the kth projection of x power n, is, so we're adding up all of these terms. So remember, each time we get another sum, we have another power of p1. So we have this power of p1, so we're adding up all of these tailing terms. Each time we go through another index, we get an extra power of p1 of x, and then each time we just have whatever this is with the corresponding power. So here we have n minus 1 for when we've done it once, and over here we're just saying, as we increase I, we'll just subtract more and more off of this power. So this is sort of our inductive formula. You could prove this by induction. It's not too difficult. It's just sort of a repeated sum and product. But from here we just rearrange these terms a little bit. So instead of having this summation in front, we actually want to put it down here in the back. So we sort of flip-flop these around. So we end up with, so this term stays the same here, and then we just have this summation across the divisors, and then we have this other summation across these I values. And so this is why we sort of set up all of our lemmas. So our most recent lemma, recall, is we have this repeated summation of two things multiplied together. One of them increases with the index of the sum, and the other one decreases with the index of the sum. But the sum of the two indices, this I plus n minus I, sums up to n. And down here, that's exactly what this whole thing is. We have this. We can think of this part as one series, and it's indexed by I, which increases with I. And then this second one, we can think of this second projection as some other series, and this decreases with I. And their sum, if we add I plus n minus I minus 1, that's n minus 1, but that's exactly the top component here. So the phi value of this whole summation is just bounded by the maximum of these two things. So whatever the phi value of this and whatever the phi value of that is. Likewise, we also have, right up here, we have, in lemma 3.3, we have this sub-additivity, and also in corollary 3.2.1, we have this, if we have some constant coefficient, then the phi value is the same. So we can actually think of this capital phi function as being sublinear. So because it's sublinear, so back down on Theorem 3.6, so we have this inductive formula, we have some expression plus this repeated sum with some constant coefficients. So remember, a is bounded by k, so we have this finite, in terms of n, as n is increasing and k is fixed. This is a finite sum of some terms, and then we also have this other sum here. So from sub-additivity, the capital phi value of this pk projection, that's right down here, capital phi of this pk projection of x power n, less than or equal to the maximum, we have the phi value of this expression, and remember this right here, this is just a constant, so the phi value of this first term is just bounded by the phi value of this part here. So we drop this part here right down here, That's the first part. And then we have this other sum, this other finite sum of terms. And so for each one of these, again, we have this constant term, so it doesn't change the phi value. And then we have for each a less than k, which divides k. And actually, here we're actually sort of having more terms. We're sort of ignoring the fact that a has to be a divisor of k, and we're just saying if a is less than k, because it doesn't matter in the end, because we're doing a less than or equal to maximum. So adding more terms than the maximum doesn't change this inequality here. So we're taking the phi value of each of one of these sums here. So we're taking a sum of this plus all of these terms. The phi value of this is bounded by, because of the sub-additivity, it's bounded by the phi of this and all the phi values of these terms here, for all the a less than k. But of course, all the phi values for here, all of these ones, these are bounded by, so we have phi value of the p1 of x power I, that's the same as this term here. And it's also bounded by, it's bounded by the maximum between whatever this is and the phi value of this. So here we have the phi value of p sub a of x power n, and that's all of these terms, so the maximum of whatever these are. And we also have here, we're saying any a less than k or a equals to 1. And the reason that we're doing a equals to 1 is because of this term and this term. So here we have this projection index equaling 1. And we're able to pull this exponent, this n, inside this first projection because our p1 function is multiplicative. So we just have p1 of x power n equaling p1 of x and then to the power of n on the outside. So these two things, because these two things are equal, we can just pull it in. And so ultimately, our phi value of this first projection is bounded by the maximum of all of these phi values. But these are just the phi values, right? So on k, these are just the phi values of the lower indices, a, which are either less than k or equal to 1. So if we just, because we've bounded the kth projection by all the lower projections than k, or 1, then induction basically just gives us that this phi value of this kth projection is bounded by just the first one, just the first term, phi of p sub 1 of x power n, because each of these p sub a projections are going to be bounded by the ones before them, and so on and so forth, by the maximum of all the previous ones. So ultimately, each projection is bounded by just the first projection in its growth. In its exponential growth. So because we have the phi of all of these projections, every single projection is bounded by the phi of the first projection, by the first characterization. So remember, the first characterization is, it's both, let me find it. Yeah, here. So the first characterization is just the supremum of the root test on each projection. And so we're saying the phi value, that is the root test of each projection, is just bounded by the very first projection. So right down here we are, yeah. So because all the phi values of the projections are bounded by the phi value of the first projection, and the phi value of the first projection is bounded by the phi value of this xn power overall, and likewise, every single one of these projections the phi value of x power n overall is just the supremum of these phi values of the projections. Then actually we just have to have the phi value of this exponential series, x power n, is equivalent to just the phi value of the first projection. So essentially what we're saying is, however the first index grows compared to an exponential, all the other projections, all the other indices, are going to grow comparable or less than that. And that gives us our overall phi value. But of course we know, because this p1 function is multiplicative, this phi value of this first projection, this is just the phi value of this exponential series, p1 of x, and then to the power of n. Well, p1 of x is a complex number, so this is just a standard root test of an exponential series, and that just gives us absolute value p1 of x, which is what we wanted to prove. So the statement of this theorem, for every x we have this equality, and that is exactly what we've concluded on. that the phi value of this exponential series, x power n, is exactly equal to the absolute value of p1 of x, so the absolute value of whatever x is on its first projection. So its first component. And this is super useful. So our corollary is related to this. Our corollary is, so for every single x in our space A, and every sequence alpha in our, which is a sequence across our space A, indexed by natural numbers, we have this equality, which is that the phi value of x power n then times alpha sub n, so if we multiply each of these sequences, this is exactly equivalent to p sub 1 of x times the phi value of alpha. And this is also, in the case that x is a real or complex number, this is exactly what you would expect from the root test. That if you multiply by an exponential, that's just exactly equal to whatever the base of that exponential is times the rest of the stuff when you're analyzing it using the root test. So sort of this x power n comes out just like you would expect in the root test. And the way to prove this, so we already know that we have sub-multiplicativity of our capital phi function. So when we multiply these two sequences, x power n times alpha sub n, the phi value of this product is bounded by the product of their phi values. So phi value of this x power n times phi value of alpha. But we, just as in our previous, the theorem we just did, we have the phi value of x power n, that's right here. This is just the absolute value of p1 of x, the first component of x. So we have this inequality first. And then we do this in cases. The first case is if the first projection is 0, the fact that our phi value is non-negative just makes this an equality. So if the first projection is 0, this right side is 0, but this whole phi value is bounded below by 0. So it's bounded below by 0 and it's bounded above by 0, so it just has to be 0, which means all of these are equivalent. So this whole expression would just be equal to this. So that would be the claim. So that's sort of the trivial base case. If P1 is not 0, so otherwise, if P1 is non-zero, well, that just means x is an A star. So A star is the set of units, and we have our characterization of A star as it's every element in A such that the first index is non-zero. So if the first index is not 0, the second case, then we can just let beta sub n, so we can take some other sequence and call it x power n times alpha sub n. So if we consider this other sequence, we can just repeat this above process. So the phi of alpha, right, is just x power negative n, because beta was x power n times alpha sub n. The phi of alpha is just x power negative n times beta sub n. So this is the phi of this thing. These are equal. These are in fact equivalent sequences, alpha and x power negative n beta sub n. But using this sub-multiplicativity property and the fact that our phi value of our x power is just this absolute value term, this is less than or equal to p1 of x inverse times the phi of beta. Because p1 is multiplicative, this means that the p1 of x inverse is actually just the reciprocal of p1 of x. That just comes from the fact that x is a unit, its first index is non-zero, and p1 is multiplicative. And so we get this equality. This is equal to, so this thing is the reciprocal of p1x, and this thing, the phi of beta, well, remember, beta is just x power n times alpha sub n. So this is just phi of x power n times alpha sub n. But because we already have this inequality here, phi of this thing is bounded, it's less than or equal to p1 of x times phi of alpha. Well, this p1 of x here is going to cancel out with this p1 of x here, and we're just going to get less than or equal to phi of alpha. So by following this whole chain of inequalities, we have phi of alpha on the left side, and we have phi of alpha on the right side of this sort of strictly non-decreasing chain of inequalities, which means we can just have to, all of these have to be equal. So in particular, this term here is equal to this. So that's what this statement is saying here. So these two, this becomes an equality. But now we can just multiply through, right? We can just multiply this whole equation by p1 of x. And so we get this term here, phi of xn, x power n times alpha sub n is equal to p1 of x, absolute value p1 of x right here, times alpha, phi of alpha. But this is the claim. This is what we're trying to prove, is that right here, this is the statement of this corollary, phi of x power n times alpha sub n is exactly equal to the absolute value of p1 of x times phi of alpha. So that's really nice. So not only do we have that these phi of the x power n is just sort of this first index, so it's exactly like, almost exactly like an exponential series for real or complex numbers. Except instead of, you know, x, we get this p1 of x, just the first component. Exactly like that, we also get the same characterization even if we multiply it by some sequence, where we might not necessarily know what alpha is. We might not know, that might not be well behaved in any way, shape, or form. But whatever its phi value is, we can just multiply through by absolute value p1 of x. There's a small amount of ambiguity here, actually, that I'm just noticing, which is that in the case that p1 of x is 0 and phi of alpha is infinity, it's actually ambiguous what this means. But I think that's because, I believe that's actually because we have some ambiguity on this sub-multiplicativity. I can tell you, though, that in this context, 0 wins. That if p1 of x happens to be 0, then this whole thing will end up being 0. But I'll need to include that, actually, as a note. So let's fix that right now. So we'll need to include that as a note, that if... Actually, it's not enough for one of them to be 0, actually. Let me also update that. So, right up in the sub-multiplicativity part here, I think I just have to restrict that neither of these are... that we don't have an infinity times 0 situation. Because in this context, we won't actually know. In the general context, we won't know... we won't actually, that's actually common, believe it or not, in letting 0 times infinity be 0. That's actually common in, I want to say, like real analysis and measure theory. If you have like Lebesgue integrals, if it has a measure 0 set, even if its value is infinity, the measure 0 part sort of wins, which is interesting. But actually, so we don't have that here. In this context, we won't actually know in general whether or not that does or doesn't work. And the reason we won't always know is because this is just a generalization of just the same root test for real or complex series. And in that case, there's an ambiguity if you have 0 times infinity. But specifically in this context, 0 wins. In this context specifically, just this one. The reason for that is kind of esoteric. I think I'm going to exclude it. I'm just going to say, you know, restrict 5 alpha less than infinity. So let's update this lemma here. We're going to assume that we don't have, you know, this thing. So actually, let me analyze exactly where. So there's definitely some error. So I think, let's see. So I know the summation is fine. That's fine. I want to say. Because even if either of these, there's no ambiguity in terms of like a maximum operation. There's just an ambiguity in terms of this here. I think actually we'll just restrict both of these phi values to be finite. If both of them are finite, then this works. I think it also works if they're infinite. But yeah. Oh yeah. It's right here, I think. we know this is less than or equal to the phi value of the product, but this might be vacuous in the case that one of them is infinite. So we actually won't know in the case of the product. In the other cases, I think it works fine. Like up here, I think it works fine. Because if there's no phi greater than phi 1, then immediately this phi 1 is greater than phi 2, and likewise. So everything here works, actually. So all this proof checks out. Because if there's no phi greater than phi 1, then phi 1 is infinite, and that's the top. So it works out here, but it doesn't work out in this product term. In this, not this one. This one. No, this one. It doesn't work out in the products. We have to assume. Yeah. We have to assume that neither of these are infinite. Or, if we do assume that they're infinite, we can have, so this is less than or equal to these products. So alternatively, we could say, actually what we're doing here is we're saying phi of alpha times beta is less than or equal to the supremum of these products such that, or sorry, the infimum of this products such that phi 1 is greater than this and phi 2 is greater than this. Well, if our set happens to be empty, then the infimum of an empty set is actually, let me think, defaults to infinity, I think. Also, give me just a sec. Okay. Yeah, so usually the infimum of an empty set is usually yeah, the infimum of an empty set is infinite because it's the greatest lower bound. So if the set is empty, everything is a lower bound vacuously, so it would be infinite. So that's actually where this proof breaks down. Because the infimum across all phi 1 and phi 2 is only the product in the case that the phi 1 and phi 2 actually exist. If the set that we're taking infimum across is infinite, then it's infinite. Yeah, so actually we have to have the product being infinity. So we'll just add a remark. We actually, yeah, okay. No, I'll just exclude them, because this is a non-bound in the case one of them is finite. It doesn't prove anything. Okay, that's nice. Okay, so we've restricted this. Both of these have to be less than infinity. We're also going to have, anywhere that we use this, we're going to have to update that condition. So I think here we just have a standard bound, and here it's fine, because phi is a finite thing. So here it's okay. Yeah, so here it's okay. And down here, we also use the product term, I think. Actually, no, we don't. We only use this summation term in this particular one, in this context. So actually it's fine here as well. So this is okay. This survives. Here, this one does need to be updated. So in the case that 5 alpha is infinite, so we'll just add that. So for x in our space and alpha with 5 alpha less than infinity, that's nice. Okay, so x in A, alpha is a sequence in A with 5 alpha less than infinity. We get this equality. So from sub-multiplicativity in the previous result, this holds because 5 alpha is finite. This 0 case works fine. And then we repeat the above result in reverse, and this works because beta sub n, or sorry, both of these are finite, and also both of these are finite. This x power negative n and this beta sub n. So then we use this same term, the same sub-multiplicativity thing, and then that gives us this, and then we multiply through by p1 of x. Cool. Okay, so this checks out. So this is fixed. So we fixed the little imprecision on that 0 times infinity. Yeah, we do have though we do have that this 0 thing wins right here. So if p1 of x is 0, then actually we do have it being 0. It's not going to be super easy to prove that. Actually, it's not going to be that hard, truth be told. But I think we'll maybe leave it out for now. No, actually, we'll include it. We'll include it. Why not? We'll say. Oh no, we'll just do it later. I'll add a to-do note. To-do. Case where p1 of x, oops, wow, is 0. So I'll just add that as a note, and that'll just be sort of a curiosity that we can use, maybe. Anyway, so continuing on, so we'll just sort of leave that for later. It's not super important. So our next theorem is take alpha in this series space, and this is for the convergence of power series. So alpha is any sequence. X and x0 are in our space A, and we have this power series, so the standard power series with center point x0 and coefficients alpha sub n, and we want to say this will actually, hold on. Okay, and we want to say that this will diverge when this inequality is held, and converge when this is the other way around. So what is this inequality here? So this is p1 of x minus p1 of x0. So this is the absolute difference between their first projections. So it's based on how close the first projections are together. If this is greater than the reciprocal of phi of alpha, then it'll diverge. And if it's less than the reciprocal of phi alpha, it'll converge. So that's what this theorem is saying. So this is essentially exactly the same as a root test. The root test for a power series says that if you're greater than the radius of convergence, it'll diverge. And when you're less than the radius of convergence, it'll converge. So that's what this theorem is proving. So in the case, let me see. in the case that phi of alpha is infinite, we actually want to check to make sure that this all checks out. We'll probably have to take that as a special case, because it might not work, but we'll see. Because we sort of have left out that case from all of these and ignored it. It should function exactly how we want it to. We shouldn't expect that something growing bigger should make it suddenly start converging. But the proof for this statement is, by all of the previous results, we have this phi value as just this product of these terms. So assuming phi of alpha is finite, then we get this absolute difference. So actually here, yeah, so this phi value of this exponential times this alpha n series is just the absolute value of p1 of the thing that we're taking the exponential out of the base times the phi of alpha. But this, so just as some clarity, this p1 is linear. So this absolute value of p1 of x minus x0, this is the same as the absolute difference of the p1 of x minus the p1 of x0, x naught. So if we have, so we'll take this first case. If we have this absolute difference being strictly greater than the reciprocal of phi alpha, then this product here, this will be strictly greater than 1, and that's just this. So this phi value will be strictly greater than 1. Using the second characterization of our phi function, we'll end up with, so the second characterization is based on limits to 0. So this phi value, if this is greater than 1, then when we multiply it by 1 to the power of n, which is just 1, then this will not tend to 0. Because if it did tend to 0, then it would be, then this would be less than or equal to 1. So by the second characterization, this exponential, these terms don't tend to 0. But the power series is just the sum of these terms. If they don't tend to 0, then the sum can't converge. There's no way that'll work. So that's the first part. That's the divergence claim, which is if we have this inequality here, then it'll diverge. And so that's this first part. The next part is take this case where we have this absolute difference less than 1 over phi alpha. So then by consequence, using the same logic up here, we have this phi value is going to be strictly less than 1. So instead of concluding that it's greater than 1 because of this being greater than 1 over phi alpha, we have this being less than 1 over phi alpha, so it's going to be less than 1. Because this is less than 1, we can find some lowercase phi in between them. So these are our terms for our power series, and we're saying its phi value is less than 1, so let's just fit some lowercase phi in between the two. Using the third characterization, so the third characterization means that we can find a bound on the terms, a bound some coefficient times our exponential. So we can find our constant such that the absolute value of all these, whatever this series is, this sequence, we can bound its absolute value by some constant a times phi power n. And so that's because this lowercase phi is greater than its phi value. And this we'll find our a coefficient so that this holds for every n. And then we can just do some approximations. So we'll take our summation here. We can bound this, the absolute value of this summation is bounded by the sum of the absolute values. And this in turn is bounded by, because this whole expression here, right from here, this is just bounded by a times phi power n. If we just factor out our a, then we have the sum of powers, which is just a simple geometric series, and we converge like this. This is valid especially because phi is strictly less than 1. So this power series converges absolutely. So in case this isn't super clear, we can also go in reverse. Because phi is less than 1, a times this 1 over phi of whatever is just equal to this a times the summation. We could pull this a in. We could replace this whole term with these absolute values, and so we know all of this converges. But then this is just absolute convergence of this power series. So that's absolute convergence. So that's the second claim, which is that when we have this, our projections are less than this 1 over phi alpha, then it converges. So essentially this 1 over phi of alpha is just the radiance of convergence of the power series, where the radius is interpreted to mean radius on the first index, where the rest of the projections don't matter, as it turns out. Yeah, and so that's also what we say down here. So this set of x, where the differences of their projections is less than 1 over phi alpha, this is just the pre-projection, so it's dependent on just the p1 of x, is the pre-projection of an open disk. So it's the, we take an open disk, so an open ball on the complex plane, with radius 1 over phi alpha, so radius 1 over phi alpha, and center point p1 of x0, p1 of x0 is here, and then we just take the p1 pre-projection, and that's because we only care about what p1 of x is. So as center point p1 of x0 and radius 1 over phi alpha. So it's just the pre-projection of some standard disk on the complex plane, which is pretty cool. And the last theorem is we have for any alpha in a sequence of coefficients alpha within our space A, we have also some x naught in our space A, and taking x inside this pre-projected disk. So this is exactly the same sentence as we just had right here, the same mathematical expression. So for let alpha be a sequence and x0 be in A and x be in this open disk, then the power series, so this standard power series, so power series in terms of x, center point x0, coefficients alpha, which we also are recognizing is just the limit of these partial initial sums. This power series converges compactly to a continuous function of x. So compact convergence means uniform convergence in each compact set. And remember, we can define uniform convergence in terms of our script A function. We also went through this proof last time. This is for each n, we let f sub n as a function of x just be these initial summations. And we know from the previous theorem, this gives us convergence. From the previous convergence, this will converge pointwise to some function f sub infinity of x, which is just the total power series. So we can consider a compact set subset to this, this pre-projected, this sort of cylinder set. Since K is closed and bounded, so K is compact, it's closed and bounded, we can find some B as being the supremum of the absolute value of, and here we're translating K minus x0. So if K is compact, then K minus, if we translate it by x0, that's still a compact set. So we take the absolute value of K minus x0, so the image with the A function, and we just take its supremum. Because K isn't compact, and it's a subset of this cylinder set, then whatever B is, its first projection has to satisfy the bounds asserted by these terms. So its first projection has to be strictly less than 1 over phi of alpha. Especially because we've subtracted this x0. So it has to be less than phi of alpha. Also, just because we have B as the supremum of this whole thing, we have the A absolute value of K minus x0, so the image of the absolute value of K minus x0 is bounded by B. So every x inside this compact set K has A of x minus x0 bounded by B, which is just this, but we replace K by x. So this bound holds for every x in K. So for every upper bound n, we can just do this approximation. So we take the absolute difference of f sub infinity, which is what our series of functions are limiting to. We subtract f sub n, and we just do some approximations. So the absolute difference of this is, so this difference is just this tail sum. So f sub n is the sum from n equals 0 to capital N. And so if we subtract that term, all those lower terms, we just get this tail sum. And it's just the power series tail sum. This is going to be, the absolute value of this is bounded by the sum of the absolute values, and also the product of the absolute values by the triangle inequality and sub-multiplicativity. So, and then this summation, because we have the absolute value of x minus x0 bounded by b, we can just replace this whole term with just b power n. So this is a uniform bound. So because we know, so our selection on b has this inequality here is true. Our selection on b has p1 of b, absolute value of p1 of b, as strictly less than 1 over 5 alpha. Because this is true, based on our convergence properties, right, this puts b inside the radius of convergence for this series. So all these series converge, is what we're saying for each n. So this is a uniform bound, right? So there's no x's here. B was independent of x. It was actually just dependent on the complex set k. So b is independent of x, and this is a uniform bound on this difference. So we have a uniform bound for f infinity, the final function, the final power series, minus f sub n. It's a uniform bound across all x in our compact set k, and also as we have n tend to infinity down here, this will tend to 0 as we take n to infinity. So we have a uniform bound independent of x and k tending to 0, and that's uniform convergence. So we have uniform convergence in the k set. Since k was an arbitrary compact subset of our domain, so we just said any compact subset of our cylinder set here. Since k was an arbitrary compact subset, then we have compact convergence. And now that we have compact convergence, so we just notice each of these initial terms, so these f sub capital N, these are just polynomials, right? It's a finite sum of just some monomial terms. X minus x0, that's linear, so it's continuous. If we multiply linear functions, that's continuous. If we multiply by a constant, it's still continuous. And if we sum up finitely many continuous functions, that's continuous. So our f sub n is a continuous function. It's a polynomial. So since each of our f sub n's are polynomials, they're continuous. And since we have this uniform convergence, compact convergence of continuous functions to our final function f infinity, especially because A is a metrizable space. Compact convergence of continuous functions implies convergence to a continuous function. So that means the power series is continuous, and that proves the claim. So we have compact convergence, converges compactly to a continuous function of x. And that's that proof. So that's sort of our whole presentation of all that we did. What we can do, though, is we can restrict, so we have sort of ignored the case where 5 alpha is infinity in a lot of these, especially in these last two. We'll still get the same results, but we'll have to use slightly different conditions. So we could, for example, modify this product proof up here. So we can modify this product proof in the case that no, actually that won't work. Let's try instead to modify this one, right, our special case. So actually if we modify this one, we can modify this for the case where 5 alpha is infinity. We can modify for that one. For the case where alpha happens to be infinity. So we can sort of update this proof. So let's see. So this whole proof works on the assumption that 5 alpha is finite. So we'll just add here in the beginning. So take the case where phi of alpha is less than infinity. And we'll remove this from our conditions. And we'll also have to add sort of a stipulation here. interpreting 0. Okay. Maybe actually we'll just include it as a second claim. Actually, that'll maybe be better. Okay, so let's actually just prove that. So we'll do another lemma. Oops. This belongs up there. I accidentally separated them. And so we'll do another lemma, and we'll do for x in A and alpha in our series space, our sequence space for these, for coefficients, with, and here we'll do phi of alpha equals infinity. Phi of, it's the same series. That's right, it's right down here. Okay, yeah, let's also do P1 of x is not 0. And then we have the same product. Oh, yeah, actually, let's do that way. Okay. This or Q1 of x is non-zero. That'll also be okay, I think. Oh, whoops. I lost a backslash there. Okay, so we'll, yeah, so we will update this. So okay. We could also update this product proof here. Okay, so Actually, this is probably fine. Yeah, I think this is okay. Okay, so we'll leave this here. All of these are fine, these are fine, these are fine. And then right here, let's just be a little more verbose. Okay, I think this is going to be good. Okay, so what we've done is we've just replaced the conditions to handle the case where it might be infinite. We've just added the condition that the product is not in indeterminate form. So we've added that condition up here on this sub-multiplicativity condition. We've just said if this is not in indeterminate form, then we get this. And by adding that in condition down here as well, we'll also get this condition. And so in order to, so we'll just make sure we'll have this here, as long as this is not in indeterminate form. So I think we can exclude this here. So yeah, okay, so this is sub-multiplicativity. So we get this sub-multiplicativity condition equals this. If p1 of x is 0, then blah blah blah. Oh, yeah, so if p1 of x is 0, then the fact that this happens makes the above inequality, proving the claim. Otherwise, we take x in a star, or we have x in a star, and it doesn't actually matter what beta sub n is, because this will be non-zero, infinite. So we can repeat this process. We'll get this is that bounded by that, which is just this, and that's bounded by this. And then we're done. Okay, so this all checks out. The only way that this will enter an indeterminate form is if we have x, p1 of x is 0, and also 5 alpha is infinity. So that's sort of our special case. I'll add that note. I'll add that as a note there. And we'll do that later. So this proof, I think this proof should still check out. So this power series diverges when this is greater than that, and converges when this is less than that. So by the previous results, we have this is equal to this. This will only apply, so this will be in indeterminate form. Yeah, okay. So if we have blah blah, okay, so we'll just say in the first case we have p sub 1, oops, absolute value p sub 1 of x minus x0 as being greater than 0. So we get this, actually, infinity greater than that, greater than 0 by the previous result, we get this inequality, or this equality actually. So phi of this power n times alpha sub n is this product. If we have p1 greater than 1 over, yeah, so actually let's put that right there. Goes out. Okay, by the previous result, we get this and that, so that this is true. Yeah, which is strictly greater than 1. Okay. Okay, yeah, so all we've done is we've just made the observation that, so in this case, the indeterminate case is actually never going to happen. The indeterminate case only happens if this difference is 0, but in this first case, if this difference is strictly greater than the reciprocal phi, it has to be positive, it has to be greater than 0. And in the second case, if this does happen to be 0, then we have to have this strictly less than phi sub alpha, in which case this reciprocal phi sub alpha has to be greater than 0. So phi sub alpha is not infinite. So this edge case never happens. So we can always take this. So that's the first case. So so by the previous result, we get this, and by the second characterization, we must have this not tending to 0, so make sure it doesn't converge. For the other claim, so otherwise, if this is less than that, this has to be greater than 0. So, oh, hold on. Okay, that's fine. Okay, and let's pull out this other thing. Take this is that. Get this. Okay, so now we've got, we're just making the observation that, all we're doing is making the observation that the edge case will never happen. So for the first claim, we just notice if this is greater than reciprocal phi, this thing has to be finite and has to be now greater than 0. So it's greater than some non-negative thing. So it's positive. And for the second case, we're just noting, well, if this thing is now non-negative and it's strictly less than this, so this has to be positive, which means phi alpha is finite. And then we can just apply the same thing, and we just apply this multiplicativity thing. We pull out our term, we say this is that, it's less than 1. So we can find our phi greater than 0, having this in between them. In third characterization, we can then find, actually let's do an and. So now we find phi greater than 0 in between them, and from the third characterization, some coefficient so then, and then we make the approximations. Cool. Okay, so this all checks out. So we've sort of handled all of this. So notice that this is the pre-projection of an open disk having center p1 x0 and radius 1 over phi alpha. And okay, yeah, and then we just have this, and this all checks out because we're just staying inside of that ball. Okay, great. So that fixes that sort of indeterminate case. So we don't have to worry about that anymore. We could probably add this other, we could prove that this does actually, if phi alpha happens to be infinite, it'll still always converge when p1 of x is 0. But I think maybe we'll just leave that for now. Because it's fine as it is. Really, we don't really need that necessarily. So we get all of this, and now I think we can just sort of move on. We can sort of go ahead with this. So what I want to do now, actually, is I want to prove one of the terms, one of the claims in our preliminary section, and put that in the appendix. So in our preliminary section, we said that where is it? Right here. Right here we said that if we have some diameter in terms of this metric distance, this will tend to 0 if and only if this other diameter does. So basically what we claimed was that we can define uniform convergence and Cauchy sequences in terms of our script A function. So what we're going to do is we're going to prove those in our appendix. So go down to our appendix A, that should be down here. We'll add a theorem, and we'll do a proof. And so the theorem is for sets S sub n indexed by n in some natural numbers, we have the following identity. And the identity is, we'll go up here, we'll copy this, and we'll just say limit as n goes to infinity of this thing in terms of S of n. This will be 0 if and only if this other thing is 0. A of x minus y. So this is our diameters. We want to say that these diameters are tending to 0 if and only if we have this sort of condition. So go down here and we'll start editing this. So that's S of n, and it's natural. We have this identity. Okay, so the way that we're going to prove this, we're going to restate the distance function. So we'll start from, I guess, the left side. So take the case that this diameter goes to 0. I'll sort of rearrange this like that. Take the first case that this goes to 0. Then for every, say, k in natural number, every index k, there is n natural number after which n greater than n has this supremum strictly less than, I think, 2 to the power of negative n. Wait, that's not right. To the power of negative k, I think. Let's pull that distance function down here, so I can see it. Okay, so what we want to do is we want to show if these distances are tending to 0 in supremum, then we want to show that these projections are also tending to 0 in supremum. So the way we can do that is, actually I have a really straightforward proof already, don't I? Proof sketch of this. Somewhere, I think it's up here, right at the top of my old draft. I think, no, not here. Not there, not there, not there. This one. Okay, so okay, yeah, so we'll do actually we can kind of just copy most of this proof. So what we're saying in this whole proof is that this sort of function here, this distance metric thing, this component, is actually increasing. If R1 is greater than R2, then this function of R1 is greater than this function of R2. So if we apply this distance function over these differences, this is just the sum of the absolute value, absolute difference of x minus y on some index. And that implies that for every index k, 2 to the power of negative k times this thing is less than or equal to this distance metric, which is then less than or equal to this summation. And this is going to work because yeah, each of these terms, this dx minus y, this will be maximized when all of these terms are as large as possible. So we're doing the summation. Okay, yeah, so we'll do that. So, okay, so take the case that this, and for every k in that, there's an initial after which this has. Actually, I don't want to do it that way, so we'll do let b sub n be the supremum of these sets. Okay. Oops. Okay, so we've got these supremums, and now we're going to say proves that for x, y, and s sub n, we have, so, oh yeah, so then, so for x, y, and s sub n, and k in natural, we have the, oh, we could also do it that way. The distance between x, actually, yeah, so the distance, okay, well, let me try it that way. P sub k of x minus y, so that's the value p sub k x minus y as less than or equal to p sub k of b sub n, so that so then do an aligned environment, and we want to write our distance metric down here. So this is just yeah, so we actually want to show a double bound. So we're going to show that these distances are bounded in terms of the a function, and the a function is bounded in terms of the distance. And the way that we'll do that is we'll show, so if the distance function is this, well, that's just bounded by we'll do pk x minus y in here, and we'll do absolute value x minus y on some index okay. So we'll take b sub n as these supremums. So for each x and y in these sets, and each index k, we have this bounded by that. So then this, which is that, is less than or equal to, so each one of these is bounded by, instead of a of x minus y, we can replace this with b sub n. And we also want to do a lower bound as being just a singular index. So we'll do, instead of k, we'll do, let's call it j. That's too many things. So bn is these supremums. So for each one of these things, we have this and that. So then, okay, let's start. We'll just start with having d as a lower bound. Okay. Function 1 minus 1 over 1 plus x is decreasing. So we can make this replacement here. And we also want, so this gives us an upper bound. So this, if we have our b sub n's tending to 0, this whole summation will tend to 0. The other way around is if we have our d sub n turning to 0, we want to put in a lower bound. So we'll do less than or equal to. And this is just any index. We'll just have some expression here. Less than or equal to 2 minus k times this whole thing. And I think let me see how that works out on the spacing. Okay, let's actually put that, so we'll have that as an equality there. And we'll do like that. Actually, I'll do it one better. Okay, that's kind of nice. And instead of k on the left side, we'll do j. Okay. So if we have b sub n going to 0, oh yeah, I do want a supremum in here somewhere. So yeah, okay. So if we have b sum going to 0, then, oh yeah, okay, we'll do that. Because I do need, this has to be, these supremum distances have to be in here somewhere, the supremum and the distance function. Okay, yeah, so this works out. So, so we end up with this sort of compounded inequality. So we have this term here as a lower bound, and this term here as an upper bound. And trapped between them, we have this supremum of the distance function. So what we want to say is, if we have the supremum of the distance function tending to 0, then we also want to say, oh yeah, okay. If we have this b sub n's tending to 0, then the supremum of the distance function tends to 0. Yeah, so we'll start by saying that. So if we have b sub n tending to 0, then the supremums of this distance function, and also, yeah, 0, which is the first direction. So our first direction is, because we have this supremum of distance functions bounded by this, then as b sub n goes to 0, this whole summation, well, it should tend to 0 as well. We should maybe be more explicit about that. So if we have b sub n tending to 0, also this summation this goes to 0 for each k. So where is it missing? Oh, it's because of the extra parentheses. Okay, so if we have b sub n tending to 0, then this tends to 0 for each k, so that this summation tends to 0. This goes to 0. Okay, so yeah, so once we form these equalities, if we have b sub n going to 0, that's the supremums of these a functions. If these go to 0, then also these, each of these terms will go to 0, and that's just a property of this 1 plus p sub k function. This goes to 0 for each k, then also this summation has to go to 0, since all of its terms are going to 0, and they're all positive. And if the summation goes to 0, then this supremum, which is bounded by that summation, that has to go to 0 as well. But that's the first direction. If these supremums of the a function are going to 0, then the supremums of the d function are going to 0. That's the first direction. The second direction will be if we prove it the other way around, which is we want to show that as our distances go to 0, also our supremums on the a function will go to 0. So as the supremum distance goes to 0. So I think the way to do that is to show that this supremum distance is yeah, actually let's do it that way. So we'll start with this. So we have this relation for every we'll do this as being an upper bound for this. So that's less than or equal to that, which is that. And we want to say oh gosh, I'll just refer to the original draft. So our distance is the summation, which is also equal to that. So that's what we have. That's just this. And we have for each k, this is bounded by the distance, which is bounded by the summation of the b's functions. Okay, that's exactly what we have. Okay, so if b sub n goes to 0, the upper bound sum is dominated by the conversion this. Terminus tends to 0. The upper bound tends to 0. Yes, so if we have this, we notice that this goes to 0 for each this, and so this goes to 0. Oops. Okay, so that's the first direction. That is what we have in this here. So, oh, that's what we're saying. Okay, so that's what we did. So the converse direction that we did originally in our draft, instead of performing some upper bound, we just assume, well, if bn is not going to 0, then just find some index k where it doesn't work. And once we find that, so up here we have okay, we'll actually do okay, so we have this bounded by that, which is that, and that's bounded by this. This is true since this function is decreasing. This is true for all x and y, so the supremum of x and y is bounded by this summation overall. If we have bn go to 0, this goes to 0 for each k, so this goes to 0 by dominating convergence, proving this supremum goes to 0, which is the first direction. So conversely, suppose b sub n does not go to 0, and find j such that one supremum on n of p sub j b sub n is non-zero, then also lim supremum across the ends of this term here that would be this. Undefined control sequence. That's that maybe? What does no? Oh, that's right. Right there. Well, that's interesting. Fascinating. Okay. So the converse is, suppose this doesn't go to 0, then find J having this. And we get supremum across n of this term cost of that's not quite right. Okay, let's actually just do it the whole way. Which a of x sub n minus y sub n not go to 0. Which are in, these are going to be in the elements in this S sub n. And we actually want P sub j of a xn minus y sub n not going to 0, and that gives us this lim supremum across n to infinity as, so 0 is strictly less than that, which is less than or equal to this diameters. I think that's enough. Okay, so the proof for these diameters going to 0 is, we'll let, for convenience, we'll do b sub n are the diameters of s sub n with respect to this a function. For every x and y inside the s sub n set, and for every index k in the natural numbers, we have this projection, p sub k, x minus y less than or equal to p sub k, these projections. This is just because b is just the supremum of these a functions. So for every, if we just pick any index j also, we can form this series of inequalities. So down here we have 2 power negative j, and then this expression where we have p sub j x minus y. This is going to be bounded below the distance function because this is just equal to this sum. So this term, this is just the j term of this whole sum, which is all positive things. But each one of these terms is bounded by each one of these a of x minus y, this p sub k, is bounded by p sub k of bn. And these functions, these are all increasing functions. So we can just replace p sub k of b sub n in place of p sub k of a x minus y. So we form this bound, this upper bound on the absolute differences of the supremum of the a function. We create an upper bound in terms of b sub n for the distance function, and we create a lower bound on sum in any given index. Then this lets us form, since this upper bound is independent of x and y, then we can actually take the supremum of these distance functions. So the supremum of these distance functions is less than or equal to this expression. And actually, we can also, if we would like, we could place this in there. So if we have b sub n going to 0, then also each of these terms are going to 0 for each index k, and this summation has to go to 0 because it's dominated by this geometric convergent sum, and it's all positive things, and they're all tending to 0. And if this upper bound tends to 0, then this lower bound has to tend to 0 as well, and this lower thing, because it's positive. That's the first direction. The second direction is, if b sub n is not going to 0, then we can find some index j, some specific j, for which this projection b sub j does not go to 0. But then we can just find, right, this b sub n is just the supremums of these absolute differences of x and y. So if the j projection of these supremums is not going to 0, then we can just find some terms, x sub n and y sub n, for which their projection of their absolute difference doesn't go to 0. And if we just plug these x sub n and y sub n in, then we get, so we have 0 on the lower bound. This is less than or equal to, this is strictly less than this limit of these functions. So this term down here, this is not tending to 0, and because this is a non-negative and strictly increasing function, then this whole function won't tend to 0. And likewise, this exponent here is just a constant with respect to n. So this whole expression, its limit supremum is strictly positive, but it's also less than or equal to this supremum. Actually, on each n, it's less than or equal to. So we can do that. So this is less than or equal to this limit supremum of these diameters. That's from this left inequality here on the left. So once we have both of these, this is some thing that has a positive limit supremum, which is a lower bound to this limit supremum. So this one has to be positive as well, which proves that this supremum does not tend to 0, which is the other direction. And so that proves us, that essentially proves that if we have some diameters with respect to the d function tending to 0, this happens if and only if the diameters with respect to the a function tend to 0. So we don't actually really need this metric function, is what this theorem tells us. We can also show Cauchy sequences and uniform convergence if we would like, so as a corollary to this. So can corollary, and we'll do proof. And what we're going to do as our corollary, so we're going to do, we'll start with Cauchy sequences. We'll say a sequence of x sub n, and in subset to our space, we'll do and in natural is convergent, goes to 0 actually. We'll do 0. Actually that's not what we want. Converges if and only if we have these, what do you want to say? The limit as some capital N goes to infinity of the supremums of these diameters, which is x sub I minus x sub j, such that I comma j are greater than n. So this limit of the supremum, so lim supremum of a difference of xi minus xj such that xi, I and j are greater than n. This limit of these supremums will be 0. It'll converge if and only if this is 0. So to prove that, recall that our pair A with D is a complete metric space. So xn converges if and only if. Oops. Converges if and only if it's a Cauchy sequence, because we have a complete metric space. So by consequence, the actual statement of that is literally this, but instead of A we have D. Then our previous theorem gives us the result when we just take our sets S of n to be these tail sequences. Actually, let me rephrase these a little bit. Okay, nice. Nice, okay, so that's Cauchy sequences. And then we can also say uniform convergence. So as another corollary, whoops, oh gosh. So a sequence of functions f sub n, which map, let's say, one domain D to our space A, for a domain D subset equal to our space, a sequence of functions converges uniformly f sub n goes to f sub infinity over D with by the metric D to some function fn goes to infinity over our domain D. Actually, if and only if, and here we want to say The definition of uniform convergence is the absolute difference of the distance function of f sub n of x minus f sub n of y, distance between these two things, such that oh, that's not what I want. What's the definition of uniform convergence? So we don't actually mess it up. Blah, blah, blah. Okay, the absolute difference from the limit is what it is. So f sub n, f sub infinity of x, such that x is in the domain D. And this shouldn't be a subtraction. It should be a comma. So a series of functions that converges uniformly by the metric D to some function fn goes to f infinity if and only if these supremums of the distance functions tend to 0. So the supremums are the distance between f sub n and f sub infinity, where x is varying across the whole domain. So this follows from the definition of uniform is that we have, so this is the definition of uniform convergence. We want to say, instead of D, we want A of the difference. Maybe we did our proof a little differently. I think in our proof, no, we did it this way. Yeah, so take our sets being the set of ordered pairs. Yeah, okay. Let me double check I've got this. We have serial equations. I want the definition for a metric space. Yeah, so we should formally oh, I don't want a net. Maybe we did do it differently in the original one. Hold on. It's really similar. Oh, okay, it's ordered pairs. We did sets of ordered pairs, or SN. Okay, let's rewrite it for that. So up here we did these distance. We just had x comma y in S sub n. Actually, we want ordered pairs of x, y. So series of sets Sn, and we'll do a squared. So that's a series of points. Yeah, and that's a lot better. Okay, so let b sub n be these for x comma y ordered pair. We have this is that, and then this will bound these. This is decreasing, so this is true for all ordered pairs. So this is x comma y, and this is just this. Mm-hmm. Instead of doing ordered pairs, because we're just ultimately taking the difference. No, I guess that's okay. I'll just leave it like that. Blah blah blah. So find these ordered pairs, giving us this here needs to be changed to ordered pairs. Proving that the supremum of these distances does not go to 0. Okay. So I've changed it. So instead of just having any x and y in these sets and using diameters, we're doing it a little differently. We're just using ordered pairs. I think we could also we could probably simplify this instead of having ordered pairs, because we're only our distance metric is linear. It's translation independent. So we could also do instead of diameters, we could do radii, so distance of all these points from 0. But I think it's fine as is. Maybe. That would be more general, actually. I'll leave it how it is, though, I think. So this gives us all this, and then a sequence of xn converges if and only if this. So recall that this is a complete metric space. Xn converges if and only if this limit is 0 in a complete metric space. So the previous theorem gives the result by taking these sets. So Sn is actually going to be xi comma x sub j, where I and j are greater than n. And for uniform convergence, so the definition of uniform convergence is that this is the limit of the supremum of these distances across x. So we can instead take S of n being the set of ordered pairs f sub n of x minus f sub infinity of x, such that x is in D. And that's just as valid. And I think that's okay. So this lets us frame uniform convergence with respect to our metric without actually talking about the metric. Yes. So those were what I wanted to prove, and we've done that. I think we can maybe look at a couple more proofs before we take a break. So let's go up to where we left off in our power series. So we had just proven that our power series converges compactly to a continuous function, and to do that we use this uniform convergence that we just proved in our appendix. So we've proven that it converges compactly to a continuous function. Now, next, what we want to do, we've also, of course, conversely, we've determined exactly where it converges, and what we want to do is next we want to do analyticity. So we've done a whole bunch of exponential things. We figured out where power series converge, where they're continuous. Next we want to prove that a power series is analytic. Using the power of foresight and also transcendental reasoning, we can actually know that when when we want to get around to, so when we're going to try to prove our power series are analytic, we can actually use the standard formula for translating a power series. So normally in real arithmetic, so real or complex arithmetic, if you've got a power series, let's say we've got some power series, summation n equals 0 to infinity, and we'll just leave it as x power n for now, and then some coefficients, alpha sub n. If you want to translate this, this can also be interpreted as, so this is summation n equals 0 to infinity of, we have, so if this is, if we label this analytic function f of x, this is the summation, we have n factorial, we have f, the nth derivative of f, evaluated at 0, or a center point, and then we just multiply by alpha sub n. So if we had sort of a normal standard power series, oh sorry, not just alpha sub n, we have x power n, alpha sub n actually doesn't need to be there. So it would just end up being like this. If you want to translate this, we could also, instead of doing 0, we can do x sub 0, and we could do x minus x sub 0. So if we assume analyticity, we would end up with this formula, right like this. If we rearrange this a little bit, so we already know, so let me put this into, so we already know that this is just, let me actually do this. Yeah, so we already know that this, if we just pull out this f sub nth derivative of f, we can actually interpret that, so we can assume, given our f has a power series representation like this, we can sort of transcendentally suppose, let's call the f nth derivative of f at x, we'll just use the standard derivative formula for a power series, and we would end up getting summation blah blah blah. So we want to do lower bound, oh sorry, I should use some k derivative, so that doesn't, no, we can use n derivative, we just change the index. So instead of n, we'll do m. So when we drop this down, this is, it's a falling product. It's some falling product of x power m minus n, because we're doing n derivatives, and at m equals, we'll do a product. So whatever this product is, it'll be m times m minus 1 times m minus 2, and so on, all the way down to m minus n plus 1. Just like that. So that would end up being what it is. Let me put these up correctly. Another way to write that is we have a repeated product. So I'll do some index I going from 0 up to n minus 1 of m minus I, whatever that is. And we can rewrite this, so this whole repeated product. We can rewrite this as, I'm going to sneeze again. Excuse me. Okay, so we can rewrite this product as a ratio of factorials. So if we had I go all the way up to m, then this would be m factorial, but we're actually going to divide that by whatever the highest thing, we would have m factorial, except we only have, oh gosh, let me just expand this out as a difference. this product, so alternatively, instead of doing m plus I, we can just do m minus I would be m minus n plus 1 up to n. Okay, like that. That's this. And we can rewrite that as, now it's m factorial divided by m minus n factorial. That's correct. Okay, so we have this repeated product as m factorial over m minus n factorial. So this would give us our derivative. We have this repeated thing as m factorial over m minus n factorial. Let me get rid of that. So this would be our nth derivative. And in order to plug this, we can now plug this in. So we get f of x is the summation with these nth derivatives. But then if we just put in this nth derivative of x naught, we get this expression. So what we want to show is that we can use this transfer power series. The f of x is going to be equal to this whole summation. Proving that is going to be really hard. I actually didn't do it this way originally. The original way I did it was very different. It was very special. But if we want to prove it directly, we could prove it by showing that these two expressions are identical. That this power series, this power series up here, is equal to this power series, this whole mess, for suitable values of x, some x very close to x0 at least, and also for some x0 very close to 0. So that's one way we could try to prove that, but proving that is going to be kind of hard. We would have to first show that this converges, for certain values of x0, that this would converge. And we would then also have to show that in addition to the fact that it converges to what we want it to converge to, which might be a little difficult. Let me think. So I think, well, while we sit on that, let's prove something easier first. Let's actually prove, we can actually prove that our power series representations are unique. I think we should be able to prove that they're unique. The way that we would do that, so normally, we do normally have, in sort of standard analysis, these power series are actually just these repeated derivatives. That the power series is always the derivatives, and any other power series representation has to have the same coefficients. If we wanted to prove that, so I have a proof of that over in my other, my initial draft. In my initial draft, we define derivatives first before power series. So we actually define, how to take a derivative in terms of a convolutional quotient. So a Dirichlet product quotient. In this case, over here for our power series in our new draft, we could probably define that. We could probably do that calculation. We could do the derivative calculation without actually formally defining what the derivative is. That's fine. I mean, it's just a limit of a difference quotient, so there's nothing stopping us from doing that. But doing that would be interesting. Okay, I think what I'm going to do is I'm going to stop the stream for now. and I will think on this for an hour, and then I will come back to it. Also, though, let me know what you think. Should we try to prove let me pull this out so you can see it a little better. Wait, yeah, go for it. Ask your question. Ask away. While you're typing that, my question was going to be, what do you think? Should we attempt to prove as opposed to normal? That is a good question. It's just well, all calculus is infinitesimal calculus. I mean, when you say calculus, like the word means infinitesimal calculus, like in common, like nomenclature. But it's kind of the same thing, which is when calculus was invented, they called it infinitesimal calculus. It was originally called the calculus of infinitesimals. Calculus actually just means like calculate. So historically speaking, they called it infinitesimal calculus, which is kind of funny. Technically, we're not using infinitesimals, right? We don't actually have any of those. We just have standard, actually, we don't even have derivatives and integrals yet. Yeah, but when it was first sort of invented or discovered, they just called it infinitesimal calculus. But it was originally called infinitesimal calculus, but now people just call it calculus. But yeah, so that's why it's essentially because these derivatives and integrals, we actually have those. So they're not in our current draft yet, but in my original draft, which hopefully, we're definitely going to get to these concepts eventually. The only question is in what order. We do have derivatives, so right here we have some function, let's have, some function mapping some domain to the arithmetic function series space, and just define this derivative as these, limits of difference quotients. And of course, in this context, quotient means cancellation in our integral domain. And these have some really nice properties. So the question that I want to ask is, I know in advance that proving this equality here, this big mess, this is going to be true. So in real or complex numbers, this is always the case. So this just is, if you explicitly write out, what is the if you have some power series. So in real and complex numbers, every power series is analytic. It's so obvious as to be almost trivial. It would seem. It's actually not obvious. It's a thing you have to prove. You have to prove that this formula checks out, or you have to prove some other method of showing that that they work. Usually, it's done using derivatives. So you don't have to go through the process of trying to find some power series to make this equal. You just use the derivative representation. Anyway, so I know in advance that this will check out. I don't know in advance how to prove this specifically without going through derivatives and integrals in our space. So theoretically, it should be possible. I think there's no reason why it shouldn't be possible. It'll just involve, a whole lots of messy calculations that I haven't done in advance. So I guess that's my question. Do you think we should attempt to sort of go through the calculus of proving this equality to prove that power series are actually analytic functions? Or in order to prove that they are analytic functions, should we instead go through derivatives and integrals and do it that way? We're going to get through derivatives and integrals either way, ultimately. But that's sort of the question I'm posing. What do you think? What do you think we should do? What do you think would be best? I guess. Because it's totally up to you, I guess. Well, it's not totally up to you, but I want your input. We could do these in either order, I think. So we could either try to prove it this way to prove analyticity, or we could prove we could go through derivatives and integrals and things like that. Thoughts, opinions, feelings? The normal way sounds good. Okay. Then I think we'll do it that way. That's how I did it originally as well. Is there an explicit benefit? I don't know yet. So I don't actually know how to perform this calculation directly, how to prove this equality directly. I'm assuming it'll work. So I know the equality is true because I've done it the other way around. I know the equality is true. And I've also proven this equality. So this is in the context of real or complex analysis. This is sort of it's not too bad to prove this equality. It's kind of a hassle, but you can do it. If you just assume, so characterize the coefficients based on the root test, and then do some approximations, and then you can show that this converges and that they're equal. So theoretically, if we follow the same sort of pattern, it might probably work out. But it might also be really gross, and I don't actually know in advance if it'll be gross or nice. And that's just something I'll have to figure out if we did it that way. The only benefit would be that, technically speaking, it would be faster. So we wouldn't have to go through derivatives on power series to know, derivatives and integrals to know that this ultimate conclusion is actually true, that we get this result out. We wouldn't have to pass through that. So technically it's a lot longer to prove it using derivatives and integrals. But just because it's longer doesn't mean it's worse. I think that sort of is the question, I guess. But yeah, so that would be the only benefit, is that we would sort of know in advance that these work out. I don't think there's actually any reason doing this in advance doesn't make the derivatives and integrals section easier. Actually, what we do in the derivatives and integrals section is very similar to actually complex analysis. The analogs are very similar. So what we do is we define the derivative, we prove some basic derivative properties. So, derivatives of a constant is 0, derivative of the identity function is 1, and we have the addition law, we have this product rule, we have the chain rule, and so on. And we sort of go through these different proofs. Derivative of the reciprocal function, that's sort of standard, that works out. Actually, this one is kind of easy even, if you know that power series are differentiable, if you use the power series representation. But all of these are pretty straightforward. There's a few harder ones, and actually, so here's a theorem which we will have to prove, but which I know in advance is going to be really easy because of the way I've set up the current draft. So this one's like half a page long. I think in the end it's actually going to end up being maybe like a quarter, like half as long as it is. But it's all pretty standard. So there's some unique things, but for the most part it's just sort of standard progression. Yeah, so none of this actually benefits from knowing power series. Interestingly, spoiler alert for the future, what we actually end up proving to prove that power series are analytic, we actually prove that every differentiable function in a neighborhood, in an open set, is analytic. And this is the same property as in complex analysis. If something is complex differentiable, then it's actually an analytic function. It's infinitely differentiable and is equal to its power series using derivatives, its power series representation at every point. And the proof is also really similar. It's almost the same, in fact. The sort of general version of that proof is essentially we have to do like some estimations and prove there's some, Scroll down. Yeah, so we have to prove some estimations and other things. But the proof is essentially the same, which is we just do contour integrals. It's actually just Cauchy integral theorem. Is we just prove, hey, if you have a differentiable function, then you can just do these loop integrals, and they just sort of zero out. Or if you do these loop integrals with a, you know, divide by this singularity, if you do a loop integral like that, you just get the function back, which is interesting. And yeah, it's just sort of progresses like that. It's very interesting. Hopefully in this draft, proving those will be faster and cleaner even, so they'll look even more closer to their analogs, without deleting too much intuition. But we'll find out. Oh yeah, this is the one. This is the theorem that proves analyticity in this original draft. So the premise is, suppose f is differentiable in a neighborhood of a point, then we can just find some open set, some neighborhood of that point, some other possibly different neighborhood of that point, where f of x is just equal to this convergent power series over that neighborhood. And it's this power series representation. It's got these integrals and these exponents. So just by taking repeated integrals of f as a function, you just get this power series representation. It's kind of neat, pretty interesting. Anyway, enough spoilers. Yeah, so okay, I think that's a good plan. I'm going to take about an hour break to eat food, and then when we come back, we can start on derivatives, and we can do those. Probably what will happen is the derivatives section will be put before the power series section. Not really for any explicit reason, but just because if we have a derivative, we don't need power series to prove anything about derivatives, but if we have derivatives, then we can say more things about power series, which is nice. So next time we'll do that, and that'll be in a little bit. So thanks for watching for now. I will be back in about an hour with another stream, and we'll do derivatives, and that'll be fun. So thanks for watching so far. Yeah, it is the exciting part. Oh, that's okay. All the streams will be recorded. They're all saved, so if you miss anything, you can go back and watch. And also, as always, I'll be posting whichever drafts we sort of come up with over time. So you can check on those as well. Anyway, goodbye for now, and I'll see you some other time in the future. In about, an hour, I'll start the stream again. Bye for now.